coastal oceanographer and as well coastal engineer. I am a visiting researcher of the School of Earth and Ocean Sciences of University of Victoria, and also I am still keeping my position in National Institute of Advanced Industrial Science and Technology. We call it as AIST, so and it is located in Tsukuba of Japan. Today I want to talk on physical aspects of the coastal environment in Hiroshima Bay. So, and at first I would like to want to create acknowledgments from these people, especially Helen Lansdowne and Pierre Eugene for inviting me this this kind of good seminar, and also Chris Yaya and Eric Kunde and many other people of University of Victoria for their kind help for starting my life in Victoria. And also many people kindly helped me, especially I would like to say thank you very much to my co-researcher for conducting a lot of joint field measurement and field works with me. So today I want to introduce a part of my own research work, and actually all of the results today I want to introduce is a result of the joint research work with my co-researchers. Okay, at first I would like to some overview of oyster farming in Hiroshima Prefecture. This is a map of Japan and the location of Hiroshima. This is Tokyo City, and Hiroshima City and Hiroshima Prefecture is located here near the coast of Seto Inland Sea. And this is enlarged map of Hiroshima Bay. You can see that many islands in the Hiroshima Prefecture, and the shape of the coastal lines are quite complicated. So, as a general information of oyster farming, so the total value of fishery industry of Hiroshima Prefecture in 2006 is almost 286 million Japanese yen. It is almost equal to 336 million Canadian dollars. And in the total value, the value of oyster farming in Hiroshima is 163 million Japanese yen, and it is almost 60% of the total of fishery industry in Hiroshima Prefecture. And also, this oyster farming of Hiroshima making up more than half of the total production of oyster farming in all of Japan. And in addition, I would like to show you that Japan has the third largest oyster production, just behind China and Korea in the world. Okay, so next slides show the this map just show the area of oyster beds in the northern part of Hiroshima Bay. The red hatched area is showing area of oyster beds such as like this, and around the islands. Around the islands, you can see a lot of the area of oyster beds, and also there is a big river whose name is Ota River. river mouth is located around here. So around the river mouth, you can see there are many number of oyster beds, and also in a bay and around the islands and in the strait, you can see a great number of area of oyster beds. Because to prevent oyster beds from natural disaster due to the strong wind and wave, and also to provide oyster beds with good nutrient from the rivers are most important things for the oyster farm. So that's the reason. So you can see the area of oyster beds around the island or the rivers. Next slide. From next slide, I quickly show you the exact situation of oyster location of oyster farming by using airplane photographs. So at first, I would like to show you the pictures around number of station. This is a number around the number of station. Picture around the number of station. So these are all of them are the oyster farming. And the second is north area of this island number 2 station. So this is also strait and open sea, and around the island coast there are many oyster farming beds. And number 3 photograph is south area of this island. You can see many types of many number of oyster farming beds, and also number 4 is the mass of Hiroshima Island, such as like this. So number 4 is maybe almost similar photograph, but as you can see, there are many oyster farming around the coastal region of Ireland. And finally, the number 6 photograph is taken at the inside of Hiroshima Bay, like near here. So, because the inside of the bay is a quite nice place to conduct oyster farming, so you can see a lot of the oyster bays, such as this. And also, I quickly would like to introduce the overview of the oyster farming as well. So, number of management body of oyster farming in Hiroshima Prefecture is in 2006 almost 398, almost 400. But actually, the number of management body took months in 1967. At that time, so the number was almost 1,000. So from 1967, it has been decreased gradually over the past 39 years. And also the number of oyster farming float in Hiroshima Prefecture in 2006 is almost 10,000. And the average number of float per one management body is 228. So one farming management body usually keeps almost 30 number of float of oyster farm. And also annual income for one family type management body in 2005 is 70 million Japanese yen, and it is almost same as 200,000 Canadian dollars. It seems to be very huge amount of annual income. But please note that 76% from income, 60% of income is coming from fishery industry, and 30% is not coming from fishery. And the ratio and the total annual income must vary strongly according to damage due to such as red dye or the harmful algal blooms or the hypoxia, insufficient dissolved oxygen water, or the storm typhoon disaster. So from now, I want to introduce the two types of causes of the trouble for oyster farming. One is the harmful algal bloom, and another one is hypoxia. So first topic is the horizontal distribution of planktonic cysts of harmful algae, Alexandrium tamarense, in the sediment of Hiroshima Bay and its physical reason. So as I mentioned before, so Hiroshima Bay oyster farming gained almost half of the domestic market share of oyster in Japan. But if the shipping of oyster to commercial market should be cancelled if shellfish toxin exceeds its threshold, such as like 4 months unit per gram for paralytic shellfish toxin. So the frequent occurrence of shellfish toxin causes local economic loss, such as 1,800 million Japanese yen loss in spring of 1992. So one research project on this Alexandrium tamarense causative species of paralytic shellfish toxin was conducted, financially supported by the Ministry of the Environment Japan. So left side pictures the example of the causative species of Alexandrium tamarense, and its size is almost from 24 to 35 micrometer, very small species in the water, and the number of cells of 10 cells per milliliter seem to cause potential to make shellfish toxic. And also it spends almost 4 years as a resting cyst in the bottom sediment, such as this. So the Alexandrium tamarense has a very unique characteristics. One is this generates cysts with very hard shell. When they are growing, condition is getting worse. So this cyst will make next generation after germination in spring. And the cyst exists around the bottom sediment 5 months of aging period. 5 months of aging period means before their germination. And also water temperature under 15 degrees keeps high germination rate. And also light condition, enough luminescence have a key role to induce germination. So this slide shows the horizontal distribution of cysts of Alexandrium tamarense in the bottom sediment of Hiroshima Bay at the 1987 and 1993 and 1998. And this is 1987 and 1993. And I would like to say the magnitude of bar chart is quite different among these 3 years, because the number of cells in one cubic centimeter is in 1987 is just up to 30, but in 1993 almost 1,000, and 1998 more than 3,000. So the magnitude is quite quite different. So I changed the scale of magnitude. So in 1987, the northern part of Hiroshima Bay, so the number density, population density of cysts in the sediment is quite low. So, but in 1997, for example, in Kure Bay and around the coast of Hiroshima, the cell density reached to, for example, 1,000 or 500. And after 5 years from 1993, so around here and Kure, this bay, the density of cells in the sediment reached almost more than 3,000. So zone with high density of the cysts spread across Hiroshima Bay from 1987 to 1998, and also head of Hiroshima Bay and Kure Bay may be a source of cysts because of the high density of cysts. And this slide shows the left side, left figure is tidal current magnitude of Hiroshima Bay. So because the one tidal component, we call M2 tidal component, is strongly dominant in this way. So I show the M2 tidal amplitude in order to show the magnitude of tidal current. So and the hatched area shows that is M2 tidal amplitude is less than 5 centimeters per second. So it means magnitude of current is quite slow. So water should be stagnant around this region. And so hatched area seem to correspond to the zone with high density of such like this region. So, and also Kure Bay has a very weak current magnitude. So this result is consistent with previous research work. The highest density of cysts are formed at the region with stagnant water of the convergence region with difference waters. So and now, but now we have a question because actually the Hiroshima Bay and the Kure Bay, the sedimentation rate is almost 111 millimeter per year. It is very high rate. And also, as I mentioned before, light condition, luminescence has a key role to induce germination of Alexandrium tamarense. So, assuming this condition, maybe the cysts should not germinate after spending aging period, 5 months in Hiroshima Bay, because they should be in the deep of the sediment without any light, any luminescence. But actually, as you can see, from 1987 to 1998, so horizontal distribution of resting cyst, high density of resting cyst spread. So at the moment, so I do not understand why such a condition has happened. So one assumption is so all the cysts made the next generation after they were resuspended into the seawater body from the bottom sediment. So this is a collateral evidence of this assumption. Because after this field of measurement, I understand that cysts were detected near the surface. This is a result of field measurement. We put the sediment trap like this at this point, and near the surface, depth is a 3 meters. We could detect the resting cysts such as this, and so the cyst can detect it near the surface after conducting this field measurement. And also, from aging diagnosis of Alexandrium tamarense in the sediment trap by special fluorescence analysis proposed by Tsukuba and Yamaguchi. We understand. So all cysts in the sediment trap near the surface were confirmed old cysts, not new. So they must come from the deep of the sediment. So the next is why the old cysts could be suspended from the deep of the sediment. So now I made another assumption. The reason is the strong disturbance due to strong north wind in winter is one of the cause of the resuspension of resting cysts. So in order to confirm this assumption, I used the observed data of resuspension during a storm typhoon passing. And also, we assume the cyst may be attached to the sediment. So, and then vertical profile of turbidity is regarded as the vertical profile of cyst density. So this is observation data of Hiroshima Bay during a typhoon, strong typhoon was passing over. So this is the wind speed, and this is the current speed, and the third one is the turbidity. Turbidity is not as the same as density of plankton cyst, but at the moment, so I assume the turbidity is the same type of data of cell density of resting cyst. And this is a level. Coastline level. So as you can see, there is a strong resuspension of the sediment due to strong wind, more than 15 meters per second. And the turbidity at the bottom of the ocean changing from 5 to 20 million howling per liter. So by using this observational data, we made a one-dimensional simple model to calculate vertical change of turbidity. So this is a comparison. This is a result of numerical simulation. Thick line is turbidity calculation result of turbidity. 1 meter bottom, 1 meter above the bottom, and 1.5 meter above the bottom. And the thin line the observation data. So the result, numerical result seemed to be very nice and good correlation with observation data. So after that, so we, by using this numerical simple simulation model, so we tested how we tested the height of resuspension of the turbidity. So you can see from the numerical model, maximum reachable point of turbidity is reached 4 meter depth around the point. And on the other hand, as I mentioned before, the plankton, all the cysts of Alexandrium tamarense were detected at the depth of 3 meters. So both results almost are approximately consistent. So the storm typhoon or the storm north wind have enough power to make this resuspension and resuspension of the sediment and resting cysts from the bottom to the surface. And also, I checked the condition of light luminescence and water temperature by using observational data. So this is a vertical profile of light condition. So the threshold of luminescence is, in this case, 10 micromole per square meter per second. And this is a season of autumn, and this is winter. So you can see the, in autumn, because due to insufficient luminescence at the bottom, so if the cyst, even though cyst is resuspended in the body water, they do not have enough light in the water column around here. And also in autumn, so temperature is more than 15 degrees, so the cyst cannot germinate in this condition. But in water season, so the water is very clear, so at the bottom there is a sufficient luminescence and temperature, water temperature is less than 15 degrees. So in winter, cyst can germinate. So finally, so I would like to conclude the reason why the resting cyst can be spreading out from 1980 to 1990. So at first, so cysts of Alexandrium tamarense in the bottom sediment, such as like this. But after happening of strong wind-induced mixing, it can be resuspended in the body water, such as like this. And if the condition of light and water temperature, and also some, if they have enough nutrient in the body water, it can be germinate and make plankton body, such as like this. And also the wind-induced strong wind, especially strong north wind, can generate vertical circulation, such as like this. So by using this vertical circulation, both cysts and plankton can travel to the another part of Hiroshima Bay, and then finally, so they create cysts again and settle down the working sediment. So this is another numerical simulation of the Hiroshima Bay under the condition of north wind of 8 meters per second. At the surface, so there is a very strong the current down to the south, but in the bottom, so you can see that very weak current, but the current direction is from south to north, like such like this. Okay, this is these are the first part of my research topics of harmful algae bloom. So the second part is hypoxia problem due to strong suspension. Because of insufficient dissolved oxygen water also has also gives strong trouble to oyster farming. So, and also strong resuspension due to disturbance may change sediment oxygen demand strongly. And if the sediment oxygen demand is too strong, so it creates a lot of amount of hypoxia water. So we made a special type of instrument such as this in order to measure continuous measurement of sediment oxygen demand. So this type of instruments can measure sediment oxygen demand every 3 hours by using the special type of measure, and so this machine keeps open the system for 1 hour and to exchange the water in the measure, and then it is making closing the system for measure the oxygen decreasing in the well. So this is one of the results of sediment oxygen demand in the Hiroshima Bay. So this is a result of oxygen demand. The averagingly, the result is almost the same, but only during this period you can see the high level, high amount of sediment oxygen demand. So actually, during this period, the strong low pressure was passing over around Hiroshima Bay. So, and this is another result of measurement. Snapshot of sedimentation on the frame of TV camera. So, photograph of A and B is a snapshot before and after a night without any kind of strong disturbance. So you can see a lot of sedimentation accumulated on the frame of video camera, such as like this. But the picture of C, D, and E and F is a snapshot on the November 15 and 18 under the strong disturbance. So in this period, so sediment oxygen demand reached a high value of 3.5 gram square per day. And you can see during this period, sedimentation on the frame became lost. So this result implied strong resuspension happened during this period. So that's the reason why the sediment oxygen demand took such a high value. Summary of my topics is such as like this. So both domination of harmful algae and time dependency of sediment oxygen demand may be strongly influenced by the resuspension of the sediment due to atmospheric and oceanic disturbances. And also through these physical phenomena, it definitely will give a strong influence to oyster fishing farming as well. So I would like to continue research on this subject of suspended particle in the coast, such as like Hiroshima Bay or another part of the region in Japan. Or if I have a chance, I would like to start some joint research in the coast of North America as well. Okay. Maybe time is rush.
We have about 5 or 10 minutes, and they may have some questions, but I mean, please just complete maybe quickly if you can.
Okay, that's all right. This is a quick introduction of my own research institute, AIST. Okay, so 1 minute. I would like to introduce. AIST has one of the governmental research institutes of Japan. So we have 6 research main fields, from geological survey and applied science to the environment energy, and life science and information technology, and also another part of the field we have. And size of the research institute is the research institute has almost 2,500 research scientists, and also we have 5,000 number of visiting researchers. And my research institute has a role of geological survey of Japan, and this research institute, geological survey of Japan, has some responsibility to conduct a geological survey of coastal areas to obtain continuous geological data from land to sea. Thank you very much.